image and self-images is too strong for the asymmetry to be eliminated by assist features. Only asymmetric illumination can achieve this. 57. Assist features may also get in few have access to power forward/ground rails. Power rails are expected to be wider, which also limits the effectiveness of using assist features by constraining the local pitch. Local pitches between 1x and 2x the minimum pitch forbid assist feature placement, as there is simply no room to preserve the local pitch symmetry. In fact, for the application to the 2-bar asymmetry case, the optimum assist feature placement may be less than or exceed the 2-bar pitch. 133, depending on the parameter to be optimized: process window area, depth of focus, exposure latitude. The optimum assist feature configuration can be very different. For example, pitch between assist feature and bar being different from 2-bar pitch, symmetric or asymmetric, etc. At pitches smaller than 58 nm, there is a trade-off between depth of focus enhancement and contrast loss by assist feature placement. 133. Generally, there is still a focus exposure trade-off, as the dose window is constrained by the need to have the assist features not print accidentally. An additional concern comes from shot noise winking. Sad smiley. 135. Sub-resolution assist features, SIFs, cause the required dose to be lower, so as not to print the assist features accidentally. 136. This results in fewer photons. Defining smaller features, see discussion in section on shot noise. As SIFs are smaller features than primary features and are not supposed to receive doses high enough to print, they are more susceptible to stochastic dose variations, causing printing errors. 137. This is particularly prohibitive for EUV, where even when the primary feature is printed at 80 mj/cm2, the SRAF suffers from stochastic printing. Source mask optimization. Pitch effect on SMO. SMO carried out gated for one pitch may have varying performance for other pitches. Due to the effects of non-telecentricity, standard illumination pupil shapes, such as disc or annular, are not sufficient to be used for feature sizes of ~20 nm or below, 10 nm node and beyond. 73. Instead, certain parts of the pupil, often over 50%, must be asymmetrically excluded. The parts to be excluded depend on the pattern. In particular, the densest allowed lines need to be aligned along one direction and prefer a dipole shape. For this situation, double exposure lithography would be required for 2D patterns, due to the presence of both X and Y-oriented patterns, each requiring its own 1D pattern mask and dipole orientation. 138, 139. There may be 200-400 illuminating points, each contributing its weight half the dose to balance the overall image through focus. Thus the shot noise effect, to be discussed later, critically affects the image position through focus. In a large population of features. Double or multiple patterning would also be required if a pattern consists of sub-patterns which require significantly different optimized illuminations, due to different pitches, orientations, shapes, and sizes. Impact of slit position and aberrations. Largely due to the slit shape, 90, and the presence of residual aberrations, 140. The effectiveness of SMO varies across slit position. 141, 80H slit position. There are different aberrations, 104, and different azimuthal angles of incidence leading to different shadowing. 33. Consequently, there could be uncorrected variations across slit for aberration-sensitive features, which may not be obviously seen with regular line space patterns. 133, at each slit position, although optical proximity correction, OPC, including the assist features mentioned above, may also be applied to address the aberrations. 142, 143. They also feed back into the illumination specification, 144, 141, 145, 146. Impact of different wavelengths. Different wavelengths effectively have different pupils, resulting in different results of source mask optimization. Since the benefits differ for different illumination conditions. 142. This would necessitate the use of different source mask combinations at each slit position, i.e. multiple mask exposures per layer. 104, 147. The above-mentioned chromatic aberrations, due to mask-induced apodization, 113, also lead to inconsistent source mask optimizations for different wavelengths, pitch-dependent. Focus windows. The best focus for a given feature size varies as a strong function of pitch, polarity and orientation under a given illumination. 148. At 36 nm pitch, horizontal and vertical dark field features have more than 30 nm difference of focus. The 34 nm pitch and 48 nm pitch features have the largest difference of best focus regardless of feature type. In the 48 to 64 nm pitch range, the best focus position shifts roughly linearly as a function of pitch, by as much as 10 to 20 nm. 149. For the 34 to 48 nm pitch range, the best focus position shifts roughly linear, lying the opposite direction as a function of pitch. This can be correlated with the phase difference between the 0 and first diffraction orders. 150. Assist features, if they can fit within the pitch, were found not to reduce this tendency much, for a range of intermediate pitches, 151, or even worsened it for the case of 18 to 27 nm and quasar illumination. 152. 50 nm contact holes on 100 nm and 150 pitch had best focus positions separated by roughly 25 nm. Smaller features are expected to be worse. 153. Contact holes in the 48 to 100 nm pitch range showed a 37 nm best focus range. 154. The best focus position versus pitch is also dependent on resist. 155. Critical layers often contain lines at one minimum pitch of one polarity, for example, dark field trenches, in one orientation, for example, vertical, mixed with spaces of the polarity of the other orientation. This often magnifies the best focus differences, and challenges the tip-to-tip and tip-to-line imaging. 156. Reduction of pupil fill. A consequence of SMO and shifting focus windows has been the reduction of pupil fill. In other words, the optimum illumination is necessarily an optimized overlap of the preferred illuminations for the various patterns that need to be considered. This leads to lower pupil fill, providing better results. 157, 158, 159, 160. Phase shift masks. Phase profile of attenuated phase shift mask for EUV. The phase profile, red, for an attenuated phase shift mask used with a partially transmitting EUV absorber does not match the ideal profile design. Dotted, due to oblique incidence illumination and absorber edge scattering. A commonly touted advantage of EUV has been the relative ease of lithography, as indicated by the ratio of feature size to the wavelength multiplied by the numerical aperture, also known as the K1 ratio. An 18 nm metal line width has a K1 of 0.444 13.5 and wavelength 0.33 Na, for example. For the K1 approaching 0.5, some weak resolution enhancement including attenuated phase shift masks has been used as essential to production with the RF laser wavelength 193 nm. 161, 162, 163, 164, 165, 166, whereas this resolution enhancement is not available for EUV. 167, 168, in particular. 3D mask effects including scattering at the absorber edges distort the desired phase profile. 168. Also, the phase profile is effectively derived from the plane wave spectrum reflected from the multilayer through the absorber rather than the incident plane wave. 169. Without absorbers, near-field distortion also occurs at an etched multilayer sidewall due to the oblique incidence illumination winking sad smiley. 170. Some light traverses only a limited number of bilayers near the sidewall. 54. Additionally, the different polarizations, TE and TM, have different phase shifts. 54. EUV photoresist exposure, the role of electrons. EUV light generates photoelectrons upon absorption by matter. These photoelectrons in turn generate secondary electrons, which slow down before engaging in chemical reactions. 171. At sufficient doses 40 EV electrons are known to penetrate 180 nm thick resist leading to development. 172. At a dose of 160 C/cm2, corresponding to 15 mJ/cm2 EUV dose assuming 1 electron/photon. 30 EV electrons removed 7 nm of PMMA resist after standard development. 173. For a higher 30 EV dose of 380 C/cm2, equivalent to 36 mJ/cm2 at 1 electron/photon, 10.4 nm of PMMA resist are removed. 174. These indicate the distances the electrons can travel in resist, regardless of direction. 175. In the most recent measurement of the significant impact of secondary electrons on resolution, it was found that 93 EV photoelectrons, from a gold underlayer, had a 1/E attenuation length of 28 nm in resist. 176. The electron number attenuation was measured from the fraction of electrons captured in an electrical current from the resist. This indicates 37% of the released electrons still migrate beyond 28 nm from the exposure release point. The more highly absorbing resist removes more light in the top of the resist, leaving less for the bottom of the resist. The larger absorption leads to larger, more significant differences between the absorbed doses at the top and the bottom of the resist. Resist depth absorption, 1/, absorption, 5/, absorption, 20/, top 10 nm 1%, 5%, 18%, 10, 20 nm deep 1%, 4.5%, 15%, 20, 30 nm deep 1%, 4.5%, 12%, 30, 40 nm deep 1%, 4%, 10%, 40, 50 nm deep 1%, 4%, 8%. In other words, the less absorbing the resist, the more vertically uniform the absorption. Conventionally, photoresists are made as transparent as possible to strive for this vertical uniformity, which enables straighter resist profiles. On the other hand, for EUV, this conflicts with the goal of increasing absorption for more sensitivity at current EUV power levels. Shot noise is another concern, to be planed further below. Impact of photoelectron and secondary electron travel on resolution. Low energy electron migration. Low energy electron travel distance, R, can reach at least several nanometers, even though the distance between electron collisions, scattering, is 1 nm. Photoelectrons have a random spread that increases with accumulated dose. The stochastic electron spread function being convolved with the fixed optical point spread function, adds variability to the actual resolution. A study by the College of Nanoscale Science and Engineering, CNSE, presented at the 2013 EUVL workshop indicated that, as a measure of EUV photoelectron and secondary electron blur, 5100 EV electrons easily penetrated beyond 15 nm of resist thickness, PMMA or commercial resist, indicating more than 30 nm range of resist affected centered on the EUV point of absorption, for doses exceeding 200-300 UC/centimeter 2.177. This can be compared with image contrast degradation reported for sub-40 nm pitches later in 2015. 178. The process of electron penetration through a resist is essentially a stochastic process. There is a finite probability that resist exposure by released electrons can occur quite far from the point of photon absorption. 179. 180. Increasing the dose increases the number of far-reaching electrons, resulting in more extended resist loss. A leading EUV chemically amplified resist exposed to 80 EV electrons at a dose up to 80 UC/centimeter 2 showed up to 7.5 nm resist thickness loss. 181. For an open source resist exposed near 200 UC/centimeter 2 by 80 EV electrons, the resist thickness lost after post-exposure bake-and development was around 13 nm, while doubling the dose resulted in increasing the loss to 15 nm. 182. On the other hand, for doses and GT 500 UC/centimeter 2, the resist begins to thicken due to cross-linking. 181. The degree of photoelectron emission from the layer underlying the EUV photoresist has been shown to affect the depth of focus. 183. Unfortunately, hard mask layers tend to increase photoelectron emission, degrading the depth of focus. The generation of photoelectrons in the photoresist itself is a fundamental part of the image formation, and is marked by a random spread which increases with dose. 184, 185, 186. The randomness of the number of secondary electrons is itself a source of stochastic behavior in EUV resist images. 187, 186. The scale length of electron blur itself has a distribution. 188, 189. Secondary electron blur versus dose. Direct photocurrent measurements have been used to obtain secondary electron yields in response to EUV radiation. Simulations roughly calibrated to this yield show that the secondary electron blur increases with dose. 190. This is associated with fewer trapping sites as dose size increased and the reactions depleting the trapping sites proceed. Low energy electron-induced events also increase in number at a given distance from the photon absorption site, as doses increase. This has been confirmed by resist thickness loss measurements as a function of low energy electron dose. 191. The dose-dependent spread of secondary electrons was also known before from electron beam lithography. 192. The increased secondary electron blur with increased dose makes control of stochastic defects more difficult. 193. Secondary electron blur versus dose. The secondary electron.
Yes, the video splits in 20 seconds. We are out of power. I need to charge the camcorder. I will just try to finish later tonight. I have to stop the video because the video splits in a few seconds.